Hello everyone and welcome back. My name is Mr. Kovalt, and in this video I am again going to show you how you can find the rate law and rate law constant with the units for a given reaction when you're given sets of data from experiments. So let's get into this. Okay, so for this problem we have to kind of first review pseudo rate law constants. So let's talk about pseudo rate law constants. When do we need to worry about or think about pseudo rate law constants? That is when you are running a reaction or experiment when you have one reactant that's changing, you're like changing the concentration over time, but then the other reactant you're keeping at a very high concentration relative to the one you're looking at, such that it's basically constant over time. It is going to be decreasing a little bit because it is a reactant, but the concentration is so large compared to the other reactant that it's effectively constant. So the way we could kind of express this is in terms of the rate law. So for example, for this reaction, we have A plus B, two reactants, and then we're going to figure out like to what order they are affecting the rate. But let's write out what a rate law would look like in a generic kind of reaction. So the rate of the reaction would be equal to some constant K called the rate law constant, and that's going to be multiplied by the concentration of A raised to some power X multiplied by B, the concentration of B raised to some power Y. And so what we need to do is we need to figure out what the orders are with respect to A and B, and that's what X and Y are. So we need to figure out X and Y, and we need to figure out what K is and the units. So you'll notice in the experiments here, experiment 1, the concentration of B is really high, right? But look at the concentrations of A. Right? A is much lower. The concentration of A is much lower than the concentration of B. So therefore, in this experiment here, B is effectively constant. So what we could do then, if B is constant and then K is constant, that concentration of B can be absorbed into the rate law constant itself. So we could rewrite this as the rate is equal to K with a little prime symbol there. So it'd be K prime times the concentration of A. And so therefore we have kind of K prime is what we call the pseudo rate law constant, right? So it's the rate law constant for this reaction with only A, because B is effectively constant. So B isn't really affecting the rate, but B is there. It's hidden in the new rate law constant, which we are marking as the pseudo rate law constant with a prime, so K prime. So that allows us to run the reaction as if B wasn't involved, right? So we can see how the rate changes with respect to A, okay? And then for this experiment, same thing, except this time we have A is at a high concentration compared to B. Notice that B, we're looking at B now, we're changing B with respect to time. And you'll notice the concentrations of B that we're working with are much smaller, times 10 to the negative 5 compared to 0.20120. So this is like 10 to the negative 1. This is 10 to the negative 5. That's like a 10-fold difference, like a difference of 10, a factor of 10,000. So in this case, when we're running this experiment, A is effectively constant. So therefore, we could write the rate law this way. Our rate is equal to the rate law constant, the pseudo rate law constant. This time, A is becoming absorbed, right? A is becoming absorbed into the rate law constant. So then we could write this as the concentration of B. So I forgot X and Y. So for the first experiment, we can look at how the concentration of A is changing over time and therefore figure out what the order is with respect to A. And then for the second experiment, we can look at the reaction with respect to time and the concentration of B. So we can see how the change in the concentration B affects the rate and therefore figure out what the order is with respect to B. And so that's what the data is for. So they tell us, again, the data has been plotted in an Excel spreadsheet, so we don't have to do that ourselves. So let's go ahead and look at the Excel spreadsheet. But before that, let me explain what we're looking for in the Excel spreadsheets. So when you're trying to figure out what the order is according to the data and you want to plot the data and look at a graph, you're going to graph that 3 times. You're going to graph it according to the concentration with respect to time. So the concentration of A or B with respect to time. That would give us the 0 order plot. Then we're going to plot it with respect to the natural log of the concentration with respect to time for both of these. And that would give us the first order plot. And then we would plot this data as 1 over the concentration with respect to time. And that would give us the second order plot. And the reason we plot it in both ways, in all 3 ways, is because the reason we're plotting it with respect to time in those 3 ways is because the slope of the line or the line equation itself will be the integrated rate law for each of those orders. So 0 order, first order, and second order. And why we're doing that is we're looking for which one gives us a linear plot. We're looking at whether or not the data points line up on the trend line, the best fit line. The graph that gives us the best linear fit for the data is the one that gives us the order. Okay, so let's look at the plots. Okay, so here we have the data. Let me get in close here. Oops, hold on a second. Okay. So here's the graphs. The top graphs are experiment number 1, and the bottom graphs are the data for experiment number 2. So if we start over here, right, so on this side, give me a second while I figure this out. So this first graph here, right here, all the way to the left, this is plotting concentration versus time. So this is your 0 order plot. And you'll notice that, see the data points and you see the trend line and the equation on top. You could see the R squared value, which is a little bit off, right? So you can see that the points are not quite on the line. If we go to the next graph here, right, so this graph, the second graph right here, you'll see that that's a natural log of the concentration with respect to time. So that's giving us our first order rate law. And so you'll see that the points there are a little bit more on the line, not quite. And then if we go to the next one over, so this one right here, that's our third graph, and that's giving us 1 over the concentration with respect to time. And you could see that that is quite linear. You can see the plots, the points are on the line, and you can see the R value is like very, very close to 1. The closer the R squared value is closer to 1, the more the points fit the trend line. And so that's a good indicator as well. So if you're ever not sure, look at the R squared values and see which one gives you an R squared value closest to 1, that would be the 1. So here, for experiment number 1, this tells us that A, the concentration of A, affects the rate according to second order rate law. So that means that the order of the concentration is of A is second order. So therefore, we can now change our X to a 2. So that tells us it's second order. Now let's look at B. So for B, that's going to be experiment number 2, because we changed the concentration with respect to the concentration of B. So we're looking at how the rate changes with respect to B. So if we look at the second experiment, we'll see which set of graphs gives us a straight linear plot. Which one does the points line up on the line? So let's take a look at those. So those are the second ones. These are the bottom ones there. So again, you can see that all the way on the left here. So this graph here, let me try from the bottom. So here, this graph here, you could see that the points are definitely not on the line very much. And so you could see the R squared value is very not close to 1, very far from 1. So it's not zero order. If you go to the middle graph here for experiment number two, that's the ln, the natural log of the concentration with respect to time. You can see that the points are pretty much on a straight line there, and the R value is 0.9998, really close to 1. And then let's go to the third graph and look at that one. So here you can see on the third graph, let me get this straight. On the third graph here, again, the points are very far from 1, and the R squared value is, the points are very far from the line, not very linear, and you can see the R value is not very close to 1. It's definitely not as close to 1 as the middle one. So this indicates that it's first order. So that means that the reaction rate is first order with respect to B, so we can then change that. So we'll just get rid of the Y, and we can put a 1 there. You don't have to put a 1, but just to be clear. So now we know the order of the reaction rate with respect to B, the concentration of B, and the concentration of A. So it's second order with respect to the concentration of A. It's first order with respect to the concentration of B. Okay, now we've got that. Great, that was easy. As long as we have our graphs, now we have to figure out what the K value is. And so this is where the pseudo rate law idea is going to be coming in. So now we can use our data and the fact what we know, right, so that the K value, the pseudo K for the experiment number 1, right? So remember, this is second order with respect to A, so therefore the units for our pseudo rate law, so the pseudo, let me come back to the graphs here. So if we go back here to the, let me go back here. So if we go back here to this graph right there, the third graph farthest to the right, you'll see that above the graph there is the equation of the line, that you can have Excel just give you the equation of the line. That line there is the line of the second order rate law, the integrated rate law. 1 over the concentration of A is equal to 10.42 times time plus the that's the y-intercept. And the important thing to keep in mind is that since this is linear, and since that tells us that the experiment, that the rate is, that the rate law is second order with respect to the concentration of A. Therefore, the slope is the integrated, the rate law constant. And in this case, it's the pseudo rate law constant. So right there, you can see, where is it? So right here, sorry. So right there is the slope. So that 10.42, that is your integrated rate, that's your rate law constant, your pseudo rate law constant. So we can use that. So 10.42, so that's going to be equal to, oops, excuse me. So let's write this out. So the pseudo rate law constant, remember I wrote before that the pseudo rate law constant is absorbing the other reactant, right? So that means that the pseudo rate law constant is equal to the actual rate law constant multiplied by the concentration of the reactant that is being absorbed. And in this case, experiment 1, it was the concentration of B, which is first order. So concentration of B is absorbed into the rate law constant, giving us the pseudo rate law constant. So that means the pseudo rate law constant is equal to the rate law constant multiplied by the concentration of B to the 1 power. So now all we need to do is plug in the values that we have. So remember, the pseudo rate law constant is from the graph. That was the 10.42. That was the slope of the line. So we put that in. That's going to be 10.42. And the units for that, since this is second order with respect to A, the units of the pseudo rate law constant is going to be molar to the minus power, or per molar. I'll talk about this in a little bit later, but it's going to be molar to the -2 power multiplied by minutes to the -1 power. Okay, so that's the units of the slope, and then again, this is going to be equal to K times the concentration of B, so that's going to be equal to K, and then the concentration of B is 2.0 molar. So we'll put that in, so 2.0 molar. So now that we have this filled in, now we can solve for K by dividing both sides by 2 molar. So divide this by 2.00 molar, divide this by 2.00 molar. Oh, sorry. This is actually, this should be a -1, not a -2, my bad. That's the unit. So the units for the slope is going to be m to the -1 power times minutes, or time to the -1 power. So sorry about that. Okay, now that I have this cancels out, of course. So now I have K, the actual rate law constant, is equal to this times this. And again, notice I'm dividing by molarity again. So this is also molar to the negative power means you're dividing by that as well. So molar to the negative power is also 1 over molar. So I'm dividing by molarity twice. So that makes this is going to be, what did I get for the answer here? 5.21. So it's going to be molar to the -2 times minutes to the -1. So there's my K value that I got from the first experiment. Now I have to do it for the second experiment, and then I'm going to average those together. So for the second experiment, I'm going to do down here. So for the second experiment, same thing. So I have my pseudo K for experiment number 2, this was experiment number 1, so I'll make that clear. So the pseudo K value for experiment 2 is also going to be equal to the actual K value, the rate law constant, multiplied this time. What got absorbed here? It's going to be the concentration of A, because in this experiment number 2, A was the reactant with a high concentration compared to B. And so this one was effectively constant and got absorbed into the pseudo rate law constant. So the pseudo rate law constant for the second experiment is going to be K multiplied by the concentration of A. And remember, the concentration of A is second order. So here we've got our equation. And so now we're going to plug in the values that we have. And again, we have to go to experiment 2 to see what the rate law, the pseudo rate law constant is. And so let's go to that one again. So you'll see again, right up here, we have the second experiment. The rate law was here. And so the rate law was first order with respect to concentration of B. And so here we have there the slope of the line. And here the slope of the line for the first order reaction is negative K. So here we have a negative number. So K will be the positive of that. So K is 0.2123. So now we will just adjust that. So here, so K2 is going to be 0.2123, and the units for the first order reaction in the slope is actually just 1 over time, or in this case 1 over minutes, or minutes to the negative 1 power. So this is going to be minutes to the negative 1 power, excuse me, and that's going to be equal to K times the concentration of A squared, and the concentration of A is 0.20 molar, so that's going to be 0.20 molar squared. And now all we need to do is divide both sides by 0.20 molar squared, 0.20 molar squared. So this cancels out. And so we have K equal to this. So when we calculate that, so from this we calculate and we get 5.31. So 5.31. And notice the units now. So here we have on the bottom molar squared, and that's the same as molar to the negative 2 power if we bring it to the top. So if we go that, it's going to be molar negative 2 times minute negative 1. So now we have our two calculations, our two calculated K values. The K value that we got for experiment 1, the K value we got for experiment 2. So now all we need to do, and notice they're the same units, so molar to the negative 2 power times minutes to the minus 1 power, and molar to the negative 2 times minutes to the negative 1. So now all we need to do is add these together, divide by 2 to get the average. So let's go ahead and do that, and when you do that, you get 5.25 or 26. So the average K, let me put it, where do I want to put average? Do I have space? Yeah. So the average K value is going to be equal to 5.31. So 5.31, 5.25, and that's molar to the -2 power times minutes to the -1 power. So here we have our average. Okay, so, but if your units, and maybe you have an answer or an answer key that are not giving you the same units. Let me talk about units a little bit. So here, let me erase this. We don't need this anymore. So the thing about molar to the -2 power is that means we can bring that down to the numerator or the denominator, because anytime you have a unit to a negative power, that actually means it's in the denominator. So if we change that, we'll get k is equal to, oh, and one other thing I want to talk about is the number of significant figures. So when we added those together, the actual number would be only 2 sig figs, because when we add that together, one of our values only had 2 sig figs, which was 1 decimal place. And so the other one had 3 sig figs, which was 2 decimal places. And when you add those together doing the average, then you have to go by the least number of decimal places, not sig figs. So since the least number of decimal places was 1, then you're limited to only 1 decimal place. So this would be 5.3 would be your final answer. So let's talk about units. Okay, so K would then be equal to 5.3. And then the molar, so since this is molar to -2, we could put that on the bottom. So it would be 5.3 molar, so on the bottom. So we could just put that on the bottom. Oops. Sorry about that. Okay, so we have molar squared. And also minutes, we have minutes to the -1. So that would be on the bottom. So we could put that on the bottom too. Minutes, like so. Notice that the units, here I'll just put a 1 there. So when it's on the bottom, you change the sign from negative to positive. If these were positive and you put it on the bottom, you change them to negative. So here we change them to positive. So now they're on the bottom. And then you would multiply by, oh yeah, it would be this way. So this would be the K value. And then you could adjust this, because we know molarity is equal to moles over liter, so you could put that down there. So then your K value is equal to 5.3 over, and then that would be moles to the second power over liters to the second power, again multiplied by minutes. And so again, that if you wanted to bring this back to the top, you would have to take the reciprocal of it and flip it, right? So then K value would be equal to 5.3, and then liters would be on the top, so it would be liters squared over, right, over moles squared times minutes. So moles squared minutes would be on the bottom. This would be on top. So that would be the units of your K value. And again, if we put this all together in our rate law, right, it should look like this. Right, so finally, the rate law, if we put it all together, the rate is equal to K value. So we're going to write that as 5.3. And that's going to be liters squared over moles squared times minutes. right? Let's put parentheses around that. And then, so that's your K value, and you multiply that by A, the concentration of A to the second power multiplied by the concentration of B to the first power. And so there we have our rate law with our rate constant and the units. And that, ladies and gentlemen, is all there's to it. I hope this was helpful. I hope that you enjoyed the video and this helped you out greatly and you learned something from this video. If you did, please like the video, share the video, hit that like button over there. Also, do me a solid, subscribe to my channel. It would help me out greatly. I would appreciate it. Also, when you do that, click the notification bell above and click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me and have a great day.